Hi everyone, welcome back to my channel. My name is Cha Cha, and today I'm going to be talking about bonds and quantum mechanics, or bond types, I should say. So first let's talk about ionic bonds. So there's super big differences in electronegativity. It's typically between a metal and a non-metal, and it fully satisfies the octet rule. So it's the full transfer of the valence electron, whereas covalent is typically when you're sharing. So you have Na and chlorine, sodium has that one electron, right? Chlorine has 7 valence electrons. So as you could see, they have super big electronegativities difference because one's a metal, which is sodium, chlorine, non-metal. They get closer and closer together, and then boom, boom, boom. Sodium is left with no valence electrons, or full, I guess I should say full octet, whereas chlorine will take that electron for itself. So they all have the same configuration of a noble gas. That makes sense. I'll erase that. Polar covalent. It's when you have large differences in electronegativity. So typically like this will be like your water, or like your hydrogen bonds. And remember, hydrogen bonds are fun. Or your dipole-dipole bonds in the rare case too. Typically this is between nonmetals just because metals can't really form bonds besides like ionic, just because they're really volatile, relatively speaking, with especially with their electronegativities. And as I said earlier, you're gonna share your valence electrons, except for it's gonna be an uneven dispersion. Because for example, when we're looking at water, right? Oxygen is a lot more electronegative than hydrogen. So it's going to want to keep um, the electrons for itself. So hydrogen will have like this small cloud, whereas oxygen is kind of a bully. So it's going to be like the big, um, most of the electron, like 90%. It's like uneven custody um, of like a kid, right? Like think of electron as a kid. So like oxygen will like keep the custody of the kid like 90% of the time. And then hydrogen, let's say like they're kind of like the weekend parent. So they'll have the kid slash electron for the other 10%. Whereas with non-polar covalent, you could kind of think of them as like they're like good co-parents. So like you're still divorced, but it's like 50-50 instead of like that 90 and 10 or like that kind of uneven split. So like there's small differences in electronegativities, typically less than 0.4 or equal to zero point 0.4. Again, it's non-metals, and then you're sharing your valence electrons, so even. So a classic example of this is like when you have the same atom, right? Like carbon, carbon, those bonds, it's the exact same element. So the electronegativity is, the difference between electronegativities is 0. So you'll have pretty easy split, like 50-50 split of your electron cloud. Um, and then coordinate bond, this is kind of the last type. So like a lot of times, like sometimes you'll see on the MCAT, it's like, oh, like you have this and this element. Is it a coordinate bond covalent or is it coordinate bond ionic? It's always going to be covalent. There's no such thing as a coordinate bond that's ionic. Um, And the what is a coordinate bond? So basically both electrons come from the same atom. So it's like here, it's really common to see this in acid-base chemistry. So it's really important in that. Typically, like you'll have some base, like in this example, you'll have hydroxide with your OH. It's going to take that proton for itself since like look here, right? Like the protons, they don't have any electrons at all. So that hydroxide will donate both of its electrons for that hydroxide in order to form that bond. And then here, it's going to be a covalent bond. So they're still sharing. They're going to act like a normal covalent bond, like a normal water molecule bond, polar covalent bond after the fact. Um, so it's going to be like that 90-10 split, like we were talking about. But yeah, just keep in mind that they're always going to be covalent. Um, Now we can talk about some quantum numbers. So there are four different types of quantum numbers that you need to know. There's n, principal quantum number, angular moment quantum number, which is L, Oopsies, I don't know why that is. And then you have your magnetic quantum number, and then you have the like spin, which is ms. Um, so N is telling us like the energy level and size of the electron clouds. Like obviously like the further down in the row that you go in the periodic table, right? Like if you have something that's like in row 1 versus like row 5, like this electron cloud is going to be much bigger just because that atom itself, like there's just more electrons, right? Like there's just more, yeah, electrons. Whereas this one, if you're in row 1, you have like only like a small amount of electrons. So it makes sense. There's just more love to go around. And then another thing just to keep in mind, this is something that you should probably memorize, is that the maximum number of electrons that could be in an atom is 2n squared. Um, and then L, the magnetic quantum number, is this, oh, not magnetic, angular quantum number. It's the specific subshell of that atom. So it's the shape of the electron cloud. So I have that over here. So your L, when you're looking at it, so it's like if you're looking at a periodic table, right? You have your S, your P, your D, and your F, which is your actinides and lanthanides down below. They're always kind of the ones that are forgotten about. Um, Here I'll like kind of draw periodic table really poorly. So this will be your S. This is your P, D, and F. So when you're looking at an S, your number is going to be 0, P over here, which is your non-metals typically. So S is typically your metals, P is your non-metals, D is your transition metals, and then F is yeah your actinides and lanthanides down here. And then this is just like kind of saying like the shape of like where you'll find the electron. Remember, like an electron is not like it's constantly moving. Like you don't really truly like we don't know where it is in space. And so for S, it's kind of more of like that just like blob shape, circular shape. This is kind of like a bowling pin. I like to think of P shape. D is like a four-leaf clover, and F is just kind of like a blob. It's just like that. It's everywhere. F is just like there's like a high chance of finding the electron in a bunch of different planes. And then L, yeah, ML is like the specific orbital of that subshell. So what do I mean by that? So like S, you have one subshell, so like if you were to fill it, P, you have 3, D 5, F 7. So it's starting from S, it's +2, +2, +2, and +2. And it's typically plus or minus L. That kind of looks like 1, but this is an L. And that's, yeah, as I said, it's the specific orbital of that subshell. Then ms is your spin. So electrons can either be +1/2 or -1/2. So like they can either be up or down. They can't be both. If you're occupying that orbital, you can't be both at the same time. So yeah, that's kind of like what I was talking about, like Hund's rule, for example. Or not Hund's rule, sorry, the Pauli exclusion principle. That's what I was talking about, where like you have to have that +1/2, -1/2 for your MS. It can't be plus plus for the MS. You must have opposite spins because this minimizes your repulsion. Remember, like an electron, it has a negative charge, right? So like negative charges, remember when you're talking about electricity, not solubility, they like repels where opposites attract. So the same direction of will maximize your repulsion, right? So it's not very stable. Remember, your just like nature in general, it wants to be as stable as possible because it wants to use the least amount of energy as possible. And then Hund's rule is kind of has like similar principles that are guiding it. So like remember, like you want your electrons to be spread out or because you want to minimize repulsion because electrons have that negative charge, right? So like when you have, for example, this is like for P, for a subshell angular quantum number of 1, which is your P orbital, you'll have each one pointing up, right? But you're not going to have like two electrons that are close together when it could spread out. So it like will maximize the distance between the charge. That is sort of what Hund's rule is saying. So an example of this is carbon. Let's talk about carbon, right? So it's 1s2, 2s2, and then 2p6. So when you look at carbon, right, it's in the second row, right? So like the second row of the periodic table. So that means it's 2 is its principal quantum number. Angular quantum number is p, which is equivalent to 1. It's in the p subshell. ML will be plus or minus that 1 value. So it's minus 1, 0, 1, and 1. And then it could either be not 2p6, not nice, 2p4. So it'll either be minus 1/2 or 1/2. So each one, when you're filling out that whole shell, have them be in the same direction too, since that's typically just how they're drawn. Minimize repulsion, and then here we go. That is kind of it. That's all I have about bonds and quantum mechanics. Hopefully that was helpful. And if you have any tips to share about how to memorize anything, please leave them in the comments. I will use it. I'm sure other people will use it as well. Once again, my name is Chacha. Have a good rest of your night.